There's a black hole in our solar system, not millions of light years away, right here, orbiting our sun, invisible, silent, roughly the size of an apple but with the mass of 10 Earths. And NASA is actually taking this seriously. I know what you're thinking. This sounds insane, but stay with me because the evidence is real and it's getting harder to ignore. For the past decade, astronomers have been tracking something strange. Objects at the edge of our solar system, billions of miles beyond Neptune, are moving wrong. Their orbits are tilted, stretched, and clustered together in ways that shouldn't be possible. It's like someone's out there pulling invisible strings. In 2016, scientists proposed an explanation. Planet 9, a massive world lurking in the darkness, 5 to 10 times Earth's mass, taking 20,000 years to orbit the sun. Teams around the world started searching. The most powerful telescopes on Earth turned toward the outer solar system, scanning, waiting, hoping. But they found nothing. No reflected sunlight, no infrared signature, no thermal glow, just silence. And that's when some researchers started asking a different question. What if we're not looking for a planet at all? What if it's something that can't reflect light, something that swallows it entirely? What if Planet 9 is actually a black hole? This isn't science fiction. This is peer-reviewed research from institutions like Harvard, Cambridge, and Caltech. And if they're right, everything we thought we knew about our cosmic neighborhood is about to change. Let's start with what we actually know. In 2014, astronomers discovered an object called 2012 VP-113. It's a dwarf planet, but its orbit is bizarre. At its closest point to the Sun, it's still 80 times farther out than Earth. At its farthest point, 452 times Earth's distance. That alone is weird. But then they found another one, Sedna, with an orbit even more extreme, swinging out to nearly 1,000 astronomical units from the Sun. Then another, and another. By 2016, astronomers had identified 6 of these extreme trans-Neptunian objects, and they all shared something impossible. Their orbits were aligned, not randomly scattered like they should be, but clustered together, pointing in the same direction through space. The odds of this happening by chance? About 1 in 15,000. Scientists ran the numbers, they built computer simulations, and every model pointed to the same conclusion. Something massive is out there, shepherding these objects into formation. Something with enough gravitational pull to influence orbits billions of miles away. Konstantin Batygin and Mike Brown from Caltech calculated what it would take. A planet 5 to 10 Earth masses orbiting between 400 and 800 astronomical units from the Sun. They called it Planet 9, and the hunt was on. But here's where it gets interesting. A team of physicists did their own calculations and realized something. From a gravitational perspective, you can't tell the difference between a 5 Earth mass planet and a 5 Earth mass black hole. The gravity is identical. So if Planet 9 exists but we can't see it, maybe that's because it doesn't shine. In 2019, researchers Jakub Schultz and James Unwin published a paper that shook the astronomy community. They argued that Planet 9 could be a primordial black hole, not the kind that forms from dying stars, not the supermassive monsters at galactic centers, something far stranger, a black hole from the dawn of time itself. Primordial black holes are theoretical objects that would have formed less than a second after the Big Bang. In those first chaotic moments, regions of space with slightly higher density could have collapsed directly into black holes. And unlike stellar black holes, these don't have a minimum size. They could be as small as an atom or as massive as a planet. The ones we're talking about? Roughly 5 to 10 times Earth's mass, with an event horizon about the size of a bowling ball. Think about that. A black hole you could theoretically hold in your hands if it didn't immediately tear you apart with tidal forces. But despite its tiny size, it would have the gravitational influence of multiple Earths. Now here's the wild part. If primordial black holes exist, there could be a lot of them. floating through the galaxy, invisible, undetectable by conventional means, and billions of years ago, one of them might have drifted close enough to our sun to be captured by its gravity. Schultz and Unwin looked at data from the optical gravitational lensing experiment, a survey that detected 6 mysterious microlensing events, brief flickers of light bending around unseen objects. The masses calculated between 0.5 and 20 Earth masses. Those objects could be rogue planets ejected from other star systems, or they could be primordial black holes. The probability of our sun capturing either one, almost exactly the same. So if we're willing to believe Planet 9 is a captured rogue planet, we have to be willing to consider it might be a captured black hole instead. And that would explain everything. Why we can't find it, why it doesn't show up on infrared surveys, why years of searching with world-class telescopes have turned up nothing. You can't see a black hole directly. It doesn't reflect light. It doesn't emit heat. From our perspective, it's a ghost, a gravitational anomaly with no visible form. But that doesn't mean it's impossible to detect. If there's a primordial black hole orbiting our sun, it wouldn't be completely invisible. It would be surrounded by something. Dark matter. Dark matter makes up 85% of all matter in the universe, and we still don't know what it is. We only know it exists because of its gravitational effects. And a black hole? That would act like a dark matter magnet, accumulating a dense halo over billions of years. If dark matter particles can annihilate when they collide, this halo would produce gamma rays, high-energy radiation that space telescopes like Fermi could potentially detect. In 2020, researchers Amir Siraj and Avi Loeb proposed another method, watching for brief flares when asteroids or comets fall into the black hole and get torn apart. These events would be rare, maybe once every few years, but they'd be bright enough to see from Earth. The Vera Rubin Observatory, which begins operations in 2025, will scan the entire visible sky every few nights. If Planet 9 is a black hole feeding on debris, Rubin might catch it in the act. There's also a more direct approach: send probes. Not all the way to the black hole, just close enough to feel its gravitational pull. By monitoring timing signals from these spacecraft, scientists could detect tiny deviations in their trajectories, an invisible mass pulling them off course. Some researchers have even proposed using precision measurements of the outer planets: Jupiter, Saturn, Uranus, Neptune. If there's a massive object hundreds of astronomical units away, it would tug on these giants ever so slightly. The effect would be small, maybe just a few meters over decades, but with modern technology, it might be measurable. The next few years are critical. The Rubin Observatory will discover thousands of new trans-Neptunian objects. If the orbital clustering is real, it will become undeniable. If it's just observational bias, the pattern will fade as we find more objects in different regions of the sky. And if Planet 9 is real, whether it's a planet or a black hole, we'll finally have the data to prove it. But let's talk about what this actually means. If we confirm a primordial black hole in our solar system, the implications are staggering. First, it proves primordial black holes exist. That opens a window into the first fraction of a second after the Big Bang, a period of cosmic history we can barely study otherwise. Second, it suggests primordial black holes could make up a significant portion of dark matter. If one is orbiting our sun, there could be millions or billions scattered throughout the galaxy. Third, it raises questions about solar system formation. How did we capture this black hole? Was it a chance encounter billions of years ago? Did it influence the formation of the outer planets? Could it explain other mysteries about our solar system's architecture? And finally, it means we've been living with a black hole in our cosmic backyard for 4.5 billion years and never knew it. Of course, we need to be cautious. The evidence is compelling, but not conclusive. Some astronomers still think the orbital clustering is a statistical fluke. Others believe there's a disk of smaller objects creating the effect, not a single massive body. And some argue we just need more data before jumping to conclusions. They might be right. Science isn't about certainty. It's about following the evidence wherever it leads, even when it leads somewhere unexpected. But here's what we know for sure. Something is out there. The math demands it. The observations support it. And whether it's a planet, a black hole, or something we haven't even imagined yet, the search is pushing the boundaries of what we thought possible. We've mapped distant galaxies. We've photographed black holes millions of light years away. We've detected gravitational waves from colliding neutron stars. But right here in our own solar system, there's still a mystery waiting in the dark. And soon we might finally solve it.